Fresnel's biprism. Figure shows an interferometer known as Fresnel's biprism. The magnitude of the prism angle A is extremely small. Part A. If S0 is a very narrow source slit, show that the separation of the two virtual coherent sources S1 and S2 is given by D is equal to 2A capital A times n minus 1. Now A is the distance between the Fresnel's biprism and the source, and we have capital A, the prism angle, and n is the index of refraction of this material that the prism is made out of. Okay, so if light comes and hits this prism at an angle theta, it's going to get refracted when it enters the prism, making an angle theta prime with respect to the normal, such that the angle it makes with this axis will be 90 minus theta prime. Now, how do we find the relationship between theta prime and theta? We can write Snell's law, sine theta because we're coming from air, index of refraction is approximately 1, is equal to n times sine theta prime. Okay, so because the angles are small, we can replace sine theta approximately with theta and theta prime, sine theta prime with theta prime. So we find that theta prime is approximately equal to theta divided by the index of refraction n. Okay, then it comes and hits this other interface between the prism and air at an angle theta x. So that's the normal with respect to the interface. And you can see from this triangle that 90 plus theta x plus 90 minus theta prime plus a should be equal to 180 degrees. So the total angle inside this triangle is 180 degrees. So let's write that down. We have 90 degrees plus theta x. Theta x is the angle with which this ray hits this normal with respect to the normal of this interface. And then we have 90 minus theta prime. And then we have the prism angle A adding up to 180 degrees. So I see that I have 180 degrees plus theta x plus a minus theta prime is equal to 180 degrees. So 180 degrees cancel. And I find that theta x is equal to theta prime minus a, the prism angle, and theta prime, remember, is equal to theta divided by n. So I find that theta x is equal to theta divided by n minus a, the prism angle a. Okay, now if this ray comes and hits this interface with an angle theta x with respect to the normal, and then it's going to refract as it goes to air again, it's going to make an angle theta double prime with respect to the normal of the surface, and that's theta double prime, as you can see from this construction, because I have 90 plus theta a plus this angle equals to 180. This is 90 minus a, this is 90 degrees, and this angle will be equal to a. So a plus theta double prime will be equal to theta triple prime, which is the angle the outgoing ray makes with respect to the horizontal axis. Okay, so if I write Snell's law at this interface, the incoming ray makes an angle theta x with respect to the normal, and the outgoing ray makes an angle theta double prime with respect to the normal. I'm going to have n times sine theta x is equal to sine theta double prime. Once again, since the angles are small, I can replace sine theta double prime with theta double prime. So this is going to give me theta double prime is equal to theta x times n. But theta x is here, theta over n minus a. So it's n times theta over n, theta over n minus a. Okay, so I find that theta double prime is equal to theta minus n times a. Now what about theta triple prime? You can see here theta triple prime is equal to theta double prime plus a. So I can write theta triple prime as theta minus NA plus A. So I obtain theta triple prime, or let's do this, theta minus theta triple prime is equal to A times n minus 1. Now, what is theta minus theta triple prime? Theta is the angle we make with respect to the horizontal for the incoming ray, and theta triple prime is the angle the outgoing ray makes with respect to the horizontal. So theta minus theta triple prime is the total deviation in the direction of this ray. So you can see that here, if I have this as my incoming ray, and if the outgoing ray is this one, okay, now this has deflected from its original direction by this angle. So how much is that angle? That is theta minus theta triple prime. So that angle is the same angle here is here. Okay, so if this is the horizontal direction, now you can see that for this construction, I have this wave coming from S0, and this is the horizontal direction. So I obtain a right triangle here, where one of the angles is theta minus theta triple prime, and this side is d over 2, because I have a symmetric situation here. The distance between virtual sources S1 and S2 is d, but the real source S0 and S1, or S0 and S2, is d over 2. So this part is d over 2. So if I write tangent of this angle, tangent of theta minus theta triple prime, this is equal to d divided by 2a, where a is this side. Okay, now tangent of theta minus theta triple prime, I can basically write tangent of theta minus theta triple prime is approximately equal to theta minus theta triple prime for small angles. And theta minus theta triple prime I found to be a times n minus 1, and this is equal to d divided by 2a. I find that d is equal to 2a capital A n minus 1 with the small angle approximation. Okay, so I have shown that the separation of the two virtual coherent sources S1 and S2 is D. It's given by 2a capital A n minus 1. Now let's move on to part B. Calculate the spacing of the fringes of green light with wavelength lambda green is 500 nanometers on a screen. B is equal to 2 meters from the biprism. Take A is 0.2 meters, capital A 3.5 milliradians, and N 1.50. Okay, so we can think of these two virtual sources as the sources of waves in Young's double slit experiment. All right, and in Young's double slit experiment, when these two virtual sources, S1 and S2, are separated by a distance d, the condition for constructive interference is found this base. So if I drop a perpendicular here, these are approximately parallel to each other. The path difference here is going to be equal to d sine theta. So the path difference between these two rays is due to this portion here, which is delta. Okay, so delta, the path difference, d sine theta, must be equal to integer multiple of wavelengths for constructive interference, so that when these two waves that are in phase to start with reach at this point, they're going to be in phase also. So the path difference should be an integer multiple of wavelengths. Now at the same time, this angle is 90 minus theta, this angle is theta. You can see that tangent of the angle theta is y, where I have observed constructive interference, the bright spot, divided by the distance between the sources, the slits, and the screen. Okay, so with that, I can write tangent theta is equal to y divided by capital R, which is also approximately equal to sine theta for small angles. And tangent theta is y over R. So I have d times sine theta, which is d times tangent theta, which is the position of the maximum divided by r. So I'm substituting for sine theta, tangent theta, y over r. This must be equal to m lambda. And for constructive interference for the next two rays, I will have another position ym plus 1 over r. This will be equal to m plus 1 lambda, which means the distance between these two bright fringes, d times delta y divided by r, will be equal to lambda. Okay, so it's m plus 1 lambda minus m lambda, which is lambda. So you can see that the distance between two bright fringes, delta y, will then be equal to r lambda divided by d. Okay, now we can substitute the numbers. In our case, what is r? R, the distance between the two virtual sources and the screen, is a plus b. So r is A plus B, which is 0.2 plus 2, 2.2 meters. The wavelength is 500 nanometers. Index of refraction is 1.5, so that we can calculate D, the distance between the two virtual sources, as 2a capital A n minus 1. Capital A was 3.5 milliradians. So this gives me 2 times 0.2 times 3.5 10 to minus 3, 1.5 minus 1 for D. And I can calculate now delta Y, capital R, which is 2.2, times lambda 500 nanometers, 510 to minus 9 meters, divided by D, which is 2 times 0.2 times 3.5 10 to minus 3 times 0.5, 1.5 minus 1. And that gives me the separation between two consecutive bright fringes to be 1.57 times 10 to minus 3 meters. All right, so in part B, we want to calculate the spacing of the fringes on the screen, and that's basically the spacing between two bright fringes. So let's recap what we did here. We have an interferometer known as Fresnel's biprism. The magnitude of the prism angle A is extremely small, and S0 is a very narrow source slit, and we have two virtual sources, S1 and S2, as you can see in this construction. First, we were asked to show that the separation between the two virtual sources is 2a capital A n minus 1. In order to show that, I've looked at the incoming angle theta with respect to the horizontal axis and outgoing angle theta double prime with respect to the horizontal axis, and the deviation from the original direction for a ray is theta minus theta triple prime. The difference between these two angles is the deviation from the original trajectory. So, and I note that if I pick the one that gives me the horizontal direction for the outgoing wave direction here, this is going to be corresponding to this angle theta minus theta triple prime. So that's the deviation of the original direction for this ray. And that is whose tangent is equal to d over 2a. Now the task is to find the angle, the relationship between theta and theta triple prime. So first I use Snell's law here, and I found that for the ray that refracts inside the prism with an angle theta prime is theta over n. Then I've used this triangle, 90 minus theta prime plus 90 plus theta x plus a is equal to 180. And I found that theta x, the angle with which this ray hits the other interface normal, is theta over n minus a. Then I use Snell's law at this interface for an incoming angle theta x, outgoing angle theta double prime with respect to this normal. And I found that theta double prime is theta minus NA. And here you can see from this construction that theta triple prime is theta double prime plus A. So I add to it A to obtain theta triple prime. And theta minus theta triple prime is A times n minus 1. Since its tangent is d over 2a, and the tangent of a small angle is equal to the angle itself, capital A n minus 1 is equal to d over 2a. D is 2a capital A n minus 1. And for part B, I want to calculate the spacing between the bright fringes on the screen. I see that these two virtual sources, S1 and S2, are basically acting like two sources of waves in Young's double slit experiment. So these are two slits, S1 and S2. And the slit separation is D. And the path difference between these two rays is D sine theta, this construction here. And the path difference must be equal to an integer multiple of wavelengths for them to interfere constructively on the screen. And tangent of that angle theta, because this is 90 minus theta, this is theta here, is the position on the screen y divided by r. So if I take this as the 0 point. All right, so the spacing between the two fringes, bright fringes, will be equal to capital R lambda over D, as you can see here. And this is also using the small angle approximation. And now I have to figure out what R is, what lambda is, and what D is. I substitute the given numbers for D, and I also note that R is A plus B, the distance between the two virtual sources and the screen, and plugging in the numbers, we obtain from this expression the spacing between the bright fringes.